Very quickly, I am a group leader at the National Chemical Laboratory in Pune. This is one of CSIR's chemistry laboratories, and it's one of the oldest in the country. So our group basically looks at questions looking at how proteins work, in particular a set of proteins called membrane proteins. And these are important because they are basically the biggest drug targets that we have today. So any therapeutic, any normal pharmacological therapeutic, there's a 1 in 2 or a 1 in 3 chance that they target the set of proteins that we look at. So, there's a very high chance that any medication that you've taken would be one of the drug targets, looking at one of the drug targets we work at. And we are a very diverse set of researchers in the group. My own group is actually called Computational Biophysical Chemistry. So as you know, we have a large partly is mainly computational, but we look at biological problems through the lens of physical chemistry, hence all this. And we have a very diverse set of people in the group, from engineers, biologists, bioinformatics people, physicists, chemists, to even mechanical engineers. And we are really trying to putting it all together to understand how, at a molecular level, where is the chemistry behind all the healthcare and the therapeutics today. So in short, that's roughly. I do come from an academic family, and my parents have been instrumental in putting science as a part of our everyday life right from the start. But definitely this particular area of, at the interface of biochemistry and biophysics that we do is something that was not actually ever discussed in schools and colleges, even at home, because these were emerging areas when I was growing up. So, these were still areas that were coming up. But I think a lot of it came from a couple of books. And one of the books that I would like to mention is the DNA Double Helix that was written by Watson and Crick. Of course, now we know a lot of baggage those people come from, but it kind of discusses the journey of how they came to it. And the way it's written, it's like a detective story, right? So I used to love reading detective stories. And that's one of the books that gave me an idea that science can be detection itself, right? It's not about the facts, it's about how you come and what you're finding out that's interesting. And so it really kind of blended in what I enjoyed about the science, but also about what I enjoyed outside, let's say, detective stories or, making a story. I was a voracious reader, I used to read everything, and it kind of put everything together. And what was really interesting is that I was reading recently a book on Jennifer Doudna, and she's one of the pioneers behind the CRISPR technology. And in one of the chapters, they also mentioned that this was a book that was for her as well, an aha moment. So I think there are different aspects of that book, which, while we know there are problematic parts, I think it's just that the way the journey was detailed that kind of said, okay, this looks interesting. So I think that was when I was, in my high school years, is when I realized that I really wanted to work at the interface of biology and chemistry. As I said, it was not always possible. So I went on to actually first working in my first degrees in chemistry. And then I decided that I do still want to work in biology and chemistry. So my second degree is in biotechnology. And that's how I've been trying to blend everything along the way. Best examples of it is that while it was an emerging field, I think I was not the one who saw it emerging. I think a lot of people, so I did my master's at IIT Bombay. And I think the faculty members there really saw it emerging. So we actually had a blended class of students from their first degree in chemistry and students from their first degree in biology. And that's kind of unusual because, if you're going for MSc physics, you expect to have BSc physics. If you go for MSc chemistry, you tend to have students doing BSc chemistry in class. So this was really a very diverse set of students we had in class from many different aspects, right? And on the first day of doing, let's say, microbiology, while the course titles were all still very known titles like microbiology, on the first day they understood and they made us actually do mathematical problems, right? They said, look, let's start by solving this equation or draw this growth curve and look at this hill equation. And that's what we were doing in microbiology, right? Not learning the names of all the bacteria and all the viruses. And that really gave us the fundamental insight of how you can really work at the interface of physics, chemistry, and biology. So I really think indeed that my time for my master's in IIT Bombay really did again put a kind of a unique perspective to it. And I think over time, people have been finding their own path in seeing how it emerges. Sometimes it swings more one way or the other. But I do put a lot of credit to the faculty members during my master's who really designed innovative courses. These were not courses that you would have in any regular, predefined coursework per se beforehand, but they were really innovatively doing it. For instance, also for our exams, we would be given academic papers. So we would have to just solve equations and look at real life data and come up with something, because these were not preset ideas. So, it's always fun to see something that's really, 6 months old and we're already working on it in a coursework. So, yeah. So I'd like to focus on one part of my research, which is on these proteins called G-protein coupled receptors. And these are GPCRs for short, right? So they actually are 30% of the targets of the current pharma industry, okay? So you probably all know somebody who has used an inhaler if you're not using an inhaler yourself. So every time you have an asthma attack and you're using an inhaler, the protein it targets is a GPCR, and that's called the beta-2 adrenergic receptor. The name is not important, but what is important is that there's a very similar GPCR, which is in our heart, which is beta-1 adrenergic receptor. And you can imagine something that's beta-1 and beta-2 are very similar, right? And when you take heart medication, that's the receptor it targets, okay? Now, these two are very similar, but you want your heart to keep on contracting so that, you can live, and you want your lung to keep on relaxing so that you can breathe. If the reverse happens, that's actually problem, and that's the diseased state. Now, these two are very similar, so which is why there's often a lot of crosstalk between these receptors. And, you may have, of course, what in the pharma industry, they're called side effects. But basically, because they're so similar, we need to know a lot more about them, how they work, how they function, in order for us not to A, have the side effect, and B, actually have it target more specifically. So for instance, my receptor, let's say in the lungs, may be slightly different than yours because we have small mutations. How do those mutations then add up, right? Because it would make it more heart-like or not. So a large part of our work is looking at a very holistic way at how these receptors work, because the pharma industry wants to only look at, very, very tiny part where the, drug goes and binds. So we look at the environment, like how does the membrane in which this protein sits, how does that act? One aspect of it is looking at how cholesterol interacts with these receptors, because they make all these little subtle differences, but they all add up, right? It's like a domino effect. So we look at how cholesterol affects these receptors. We look at how other lipids affect these receptors. We look at how mutations affect these receptors. And then we are able to tell you holistically, right? We can predict them through our computational methodologies. Let's say, whether a certain drug would be the best for this kind of a scenario, or would there be other effects that come in, and the crosstalk between this receptor and other receptors, and so on and so forth. So I think this just adds up to the whole part of it. The larger picture is, of course, looking at, a larger systemic effect of drug design. But I think I would rather try to look at it more from a mechanistic perspective in understanding how these receptors work, rather than immediately say, I want to design a drug. Because that's what the pharma industry has been doing, spending millions and trillions of dollars for decades, and they haven't really come up with something which is really a very holistic, systematic perspective. So we look at all the different aspects and try to understand and give idea of how these can work. Now you can imagine that there's a very detailed chemistry, and these are really highly resolved things. So, you have small atomic changes that adds to all this. So one hydrogen moving here, one oxygen moving there, one carbon moving here can change everything. So experimental methods right now do not have the resolution to look at this in the holistic way, right? So, we use usually computational tools. We have a whole range of tools, multi-scale simulations. We're also going towards machine learning to try to identify what these small changes, what these patterns actually make in the larger picture. So we have been looking at, the one I gave you the example of in the heart and in the lung. There are only two receptors that we look at. We actually look at many more receptors. So our group has been looking at this receptor cholesterol interactions, and we have been working on it for the last few years. And this is something that's actually made a global impact on the work and looking at how these cholesterol interactions work. Because, for instance, you would imagine cholesterol is bad for you. That's what everybody tells you, right? Stop having cholesterol, have statins, don't use. But, our collaborators in CCMB in Hyderabad, they have shown experimentally, and we've actually given the real molecular mechanism how in some cases you actually need cholesterol for the receptor to work, right? So you cannot get rid of cholesterol completely, you need to have a balance in the amount, and that's what we show where the balance lies. And this is really interesting because, our brain cells actually have 40 to 50% cholesterol. Again, something nobody will tell you directly when they tell you, no, cholesterol is not good for you, right? It has to be good for you because 40 to 50% of your brain cell membrane is cholesterol. If it was zero, then all your receptors in the brain, all the GPCRs, so these are all the neurotransmitter GPCRs, like the serotonin 1A receptor, that's something which we work on a lot. So these serotonin receptors actually need cholesterol to function. So we can show where cholesterol interacts with this, how it changes, how it binds to serotonin, which is important for our neuronal signaling, but it's also important, let's say, perhaps for other drugs that bind, let's say drugs for depression and other effects. So we are really looking at this interaction of the receptors, GPCRs. It doesn't matter which pathway they are, but receptors with their environment, with other proteins, and within themselves with, different aspects of the same protein. For sure, we are saying one size does not fit all, but, we are still far from going from our labs, our computational and experimental labs, to the bedside. I think those steps still have to be taken because it's a very, very long process, right? But our work really shows that, things are very much tissue dependent. So, we do suggest that, let's say the same receptor, which is in your brain and in your stomach, your gut, they actually have different environments, so they will react differently. But also some of the drugs in the future could be age dependent, mutations are obviously very personalized, and we have shown definitely that asthma medication is, would work adversely with certain mutations versus not. This is something doctors actually right now do very ad hoc, right? Or this medication doesn't suit you, just try another one, right? So one of the projects that we had been trying to get together, of course, that's not really working out right now, is try to modulate, get genetic profiles of people, get more profiles of people, and try to correlate if we can actually, rationalize drug regimes, right? Because drug dosage would be different. So, yeah, so definitely, I think overall we can say one drug does not fit all. But to actually get it to working, it's still work in progress. So I think people know this a lot in cancer right now. I think that's really been pretty well studied by now. When you have a cancer diagnosis, the first thing they ask you to do is to do genetic mutation tests, right? So then they would be like, okay, if you're HER2, then you do this. If you're that, you do that, right? So what we are trying to say is that we need to do this for many more diseases, including, respiratory diseases, heart diseases, and not just look at mutations. That's something people have understood, but also look at the environment. What are the lipids that are involved over there? Try to consider also cholesterol regime. So this is not the free cholesterol, that is what your HDL and, all the bad and good cholesterol comes from the free cholesterol, but look at the cholesterol in the cells, in the cell membranes, look at the different lipids in the cell membranes, and all of that together would actually come up with your best regime in the future. So, but that's still a few steps. So I think we are still trying to give very detailed mechanisms about why this happens, how this happens, and then the next step would be to actually take it to regulatory systems in the future through other people and other systems where they could then translate it to the bedside. influences, as I said, have been my parents, they have been books, and they have been faculty members, especially at IIT, where I was a student. So I think these are the people who always nudged me. I think nobody ever said, do this. That was sure to make me not do something. But these little nudging along the way, introducing me to new fascinating aspects, as I said, I was a voracious reader. So the most exciting thing anybody could do for me was to give me a new book, right? So I think that was really my influence. I mean, so much so that like my parents had to bribe me with books, right? So once I got really hurt, I had a pretty bad accident and I needed to get injections, and I was in like class 4 or 5. And the way I was told is, okay, if you don't try, you'll get this book, right? And then if I did well in studies, my school also did that. So if you were in the top whatever percentage, and it was a very, very flexy percentage, right? So the prizes were always books and we could choose our own books. So books, I think, have been really the one way. The second part, coming to failure, and I do think this, I've been thinking about it a lot. I think there has never been a real failure, because as a scientist, we face failure every day in the laboratory. We face failure every day, our manuscripts get rejected, and we always find a way to take that into a better aspect, right? So in a way, perhaps me not doing biochemistry for my first coursework was a failure in some ways. Of course, I was then doing chemistry, and we always looked at the positive perspective of that. But I do think what has taught me is that there is really nothing called a failure. It's always what you learn from it and take it ahead. And this is something I really try to instill also in my research members, because really at the laboratory, you cannot let a failure get the better of you. Your experiments will not work. Your code will not run, you will not get the data that fits the current model beautifully. And those are the most fun things that happen, right? If you get data that's so shocking, that's where the fun of it lies, and that's when you start thinking of something else. When we give manuscripts, we've finished the work, it's been a long, hard journey. We sent it off to a journal and immediately they reject it. And that's very, very common in science, okay? We get journal rejections all the time. You just can't take it. So usually we take on their critique on board and we just send it somewhere else, which is perhaps a better fit to the audience, or perhaps we overlooked one aspect, we just add that in and we send it off again, right? So I think that's more or less how I look at failure necessarily than one aspect, which was a real failure. But it has always been a part of my life to also balance everything else that comes with it, because as I said, I do work in a very diverse area, right? So I need to know physics, chemistry, biology, programming, maths, some amount of statistics, and obviously I don't know all of it, right? And this has also been a part of my personal life as well, that I don't always fit one line. I do everything around it, and I try to put all of that together. So that's really how I see failure, that, I absolutely do not know everything in chemistry, physics, biology, all the things that I'm supposed to do. I know some bits. Actually, when I sit on interviews right now for chemistry entrance exams at our institute, I'm always learning new things, because I have, of course, forgotten all my chemistry from the very conventional part of it. So so not trying to be conventional and add everything from different aspects. To be a bit more ambitious, because basically to get out of my comfort zone a bit. So because I have been, as I said, wanting to work in this interface of biology and chemistry since I've been in high school, and I've never really digressed from it. I'm still continuing to work in that interface. So I just think it would have been interesting. Over time, I have learned a lot of other things, and I have looked out of the box. As I said, you need to pick up things along the way. Would have been very interesting if I'd done it way off earlier, right? If I had, done a lot of courses in engineering. Even though I want to work in biology and chemistry, that's fine. But I just go out of my comfort zone and do more things because they all help all the time later on. I think I'm most proud of the people I mentor today. So my research group, as I said, is about 6 to 8 PhD students and 2 to 3 postdocs. For a short while, we had only women researchers in the group, and this is unusual because while this is a partly biology and it is usual to have women, but it's unusual in a computational lab, it's unusual in chemistry labs, it's unusual in physical chemistry labs. And a lot of the students I mentor, they come from very varied backgrounds. And when they come, I think they're always never as secure in what they want to say and how they want to say it. They're all exceptionally brilliant. But I think it's really, I'm proud of the fact that I can give them the space to grow as researchers and really get the confidence to go and discuss with whoever that is in the field and have the strength in their science. And this is especially for women researchers. Of course, I have also young boys that I mentor, well, men that I mentor as well now, but I think I'm extremely proud of many of the young women researchers that I do mentor and who then go on to build that confidence arc. For instance, if we are at a research conference, and they are presenting their scientific posters, it doesn't matter who is in front of them. It could be a Nobel laureate, and we have had people like that. It could be the top person in their particular field, or it could be another young graduate student. They are able to take their learning, their science, show the maturity and responsibility, and discuss that in the best way possible. That's a question actually we were discussing the other day with a colleague of mine, right? Why does this happen? It does happen actually, I think, when they first come in, they don't always come in saying, I want to work with her, right? But you have your first discussion, you meet people, you see how comfortable you are in that, right? And then if you see, yes, you are comfortable, you move on further, right? That's one part of it. The second part of it is also the flexibility that I give people. A lot of people would have left. Let's say I had this amazing PhD student. She graduated last year. And during the course of a PhD, she had many personal, milestones in her life, which also meant that she needed to have a lot of flexi times. In fact, for about almost 6 months to 1 year, she was not even in the same geographical location as me. But she would continue doing her PhD. We would talk late nights, early mornings, whatever was convenient, try to discuss in the best possible way so that I'm able to support the fact that she needs those flexi times. And at the same time, she's able to give me back the best that she can do scientifically. So I think it's not always the first thing that someone says, oh, this person is someone I want to work with. But you come, you see your compatibility, you move on, and you see that, if you go to somebody and say, okay, look, I may be on a 6 to 8 month leave in the middle of my PhD, most people wouldn't agree, right? And so on and so forth. But I think she has had this amazing journey. And in fact, during her PhD defense, the external was like, oh, wow, you've answered every question. This has been great, And we would not have envisaged that at the start of it, right? It's the journey that we have together. So I wouldn't say it's only me. I would say it's how two people take the journey together towards that goal. Because in a PhD, unlike a master's, it's not, it's really also about how you work together. It's not a one-way street. I am not really giving them anything. I'm just giving them advice, and they are the ones who are doing the work. So everybody goes through stress and trauma. I'm sure if you ask my group as well, they'll be like, oh my God, we are very stressed, I think that's something that is part of it. But how you handle the stress, how you deal with your successes, and how you deal with your challenges, I think is what changes the balance, So in fact, the researcher that I was talking about, she now works at a startup. She had actually started a research program somewhere else. She quit that and then she joined me, I'm sure she didn't know about me really before she joined me, but she knew that the other research program was not a fit for her. and we discussed and we grew together and we figured out a project along the way and so on and so forth. So yes, stress, I mean, I may not want to stress people, but I have to lay a certain standard. And if I don't do it, our reviewers, our project managers, everybody would lay that standard. So, stress is a part of it, especially because, it's how research works, because a priori, I don't know what's going to work and what's not going to work. So I think we are all stressed. It's how we handle that stress. As you said, the environment that you create, the discussions that you have around that environment that you create, I think all of that adds up. And everybody's journey is slightly different, and actually everybody wants something slightly different. It's not that you can just set, okay, I want to set my environment to be very relaxed, and it is going to be that. Some people may not want that relaxed environment. They may want to be actually on their toes. And in fact, earlier this year, somebody told me, look, I need to do something a bit more proactive. So I'm like, okay, why don't you come up with weekly reports? So earlier we would be only having informal meetings. Now we formalize that. So the formal meetings would be less often. So that would be every 2 to 3 months and then every 6 months. But now we have formalized those meetings for this person every week because that's what works for them. So I think it's not just about me creating something, but me working with them to create what works for them. So I think that's important. So yeah, when I mentioned this all-women team, and I mentioned this specifically because I was an invited speaker in Paris. This was 2 years ago. And that was a very interesting meeting because it was mainly a French meeting and they only had a few international speakers. I think there were 5 international speakers they had invited. The first one was a Nobel laureate. The last one was me, right? So somewhere in the middle, we all fitted in. And when I had my last acknowledgement slides and I had the photograph of my team, they were all women. Everybody came up to me and asked me, how come that's true? Because a lot of the, images you saw before in the other talks were all male teams often, Nobody ever comes up to them and asks, why do you have an all male team, right? So that's interesting. Another point that they pointed out, which again, I'm not sure fully I agree with, is they were asking me whether it's because men are not as comfortable, young men are not as comfortable working with women mentors, and that's another aspect that you want to work towards. And this is something where I do feel that, we need to evolve a lot of the ways that we do science. Because if you meet some of the older scientists, many of them will say, oh, my research group is like my family, and we do everything together, we do everything. But you can't do that because, there is inherently a difference in the way somebody treats their mother versus their father, right? So if you think of your research group as your family and say this is a friendly environment, I think that inherently gives a disadvantage to young women mentors, and that's where you have to change the whole system as such. So I mentor not just students in my group, I mentor many other women students across groups. So I have a collaborator, he's very senior and he's not a woman, as you can understand. And I do mentor a lot of his students as well, right? I mean, they're more friends of mine by now, but I do mentor them and discuss different aspects of it. So I think it's not just about me, it's about the entire environment that you create around it, which helps. So they're really happy to work with him, no doubt about it. I'm very happy to work with him. But I think there are certain, issues that you always need to find good mentors, good discussions, and see what works for you.